T-minus 10, 9, 8, 7, 6, 5, 3, 2, 1, 0, and liftoff.
The main goal of every rocket engine is to generate a lot of heat and pressure and then convert that into workable thrust. The conversion of which is done by the rocket's nozzle, which more often than not will be a bell nozzle. The heat and pressure are made in the combustion chamber, after which they pass through the converging section of the throat and become supersonic. There's just one problem. When the exhaust pressure at the end of the nozzle gets below the pressure of the outside ambient air surrounding it, the ambient air starts to squeeze in on the exhaust gas. When that pressure gets even lower, the squeeze will cause the exhaust to peel off the nozzle walls and form random shockwaves and spikes that can tear apart the engine. But there's a solution. What if you turned an engine inside out and made it so the ambient air pressure is actually squeezing the exhaust in against the nozzle instead of squeezing the exhaust away from the nozzle? That's the essential concept behind the Aerospike nozzle. The nozzle basically forms a perfect nozzle at every altitude. Which brings me to my project. My name is Afro Panda, and my project aims to solve for empirical performance discrepancies by designing and optimizing a toroidal aerospike nozzle. I used a systematic approach to develop my design, which allows me to keep track of the engineering design process and achieve my goal. The end result should be a performance-optimized nozzle with an ideal truncation and an ideal contour. When it came to this project, I had to choose between optimizing a toroidal and a linear aerospike. In the end, I ended up choosing a toroidal aerospike because the linear aerospike gave more points of failure, had more weight, and was harder to steer, which as a result gave an overall worse performance. Phase 1. The code and contour generation. In the 1950s, an aerospace engineer named G.B.R. Rao developed a method for determining the nozzle contour that would produce the maximum thrust for any given nozzle ratio and length. For the first part of my project, I wanted to use this theory to develop the optimum contour for my aerospike design. I wanted to generate a program that would output a series of coordinates for a contour to maximize thrust, but instead of a de Laval nozzle, I wanted to apply Rao's method to an aerospike nozzle. Taking reference from a 1963 NASA contract study that outlines a similar objective in Fortran 90, the program was designed to work in three main parts. First, the control surface of the nozzle was determined by Lagrange multipliers to obtain the optimum thrust. Then, the flow field properties were calculated by using a method of characteristics, and then finally, once the control surface had been generated, the streamline that passed through the end point of the control surface formed the plug contour. In short, the program utilized a series of equations that allowed for the creation of the control surface and the determination of the right and left running characteristics. From there, the coordinates of contour equation was recursively repeated using the sonic line as a starting point to output the coordinates of the contour. Using these coordinates, I was able to generate a 3D model for the aerospike, which I then 3D printed for Phase 2. Phase 2. Truncation. Truncation means to cut off or shorten something. In regard to aerospikes, if the spike is truncated, you get the benefit of comparable or improved performance at a lower weight. Using the 3D printed models with varying truncation levels at 20% increments, I tested them in a wind tunnel and used a manometer and a force load cell to measure the forces acting upon the object and calculate the drag coefficient for each nozzle. While footage of one of the trials of experimentation plays on screen, I'll go through the wind tunnel testing materials and procedures employed for this experimentation. So for the wind tunnel testing materials, I had the 5 3D printed nozzles at the 20% truncation increments. I had 1/4 inch and 1/2 inch drill bits. I had 1/4 20 screws and nuts. I had the level to ensure that the nozzle was level in the wind tunnel, and I also had the strut for the nozzle attachment in the wind tunnel. The two main instruments used for data collection were the manometer for pressure measurements and the force load cell, which allowed me to quantify the forces acting upon the object by the wind. Now to move on to the wind tunnel testing procedure. The first step in my procedure was to measure the screw points on the strut. From there, using those measurements, I would use the drill bits to drill holes in the nozzle so that they can be attached to the strut via the 1/4 20 screws and nuts. From there, using the nozzle attached to the strut, I would place the nozzle in the wind tunnel and tighten the set screws to ensure that the nozzle would not fall off during experimentation. Then I would use the level to ensure that the nozzle is level, and I would test to make sure that the nozzle is secured correctly. Then I would close the wind tunnel window. From there, I would zero the force balance and measure the initial operating conditions. This would be the pressure in inches of mercury, and it would be the temperature in degrees Fahrenheit. From there, I would initialize the voltage program and start recording. I would wait for 1 minute to allow the voltage program to get initial data. From there, I would start the tunnel. After starting the tunnel, I would set the speed to speed setting 5. Speed setting 5 offered a wind speed of around 480 feet per minute. From there, I would wait for 1 minute, and then I would record force and water level. Then I would repeat steps 11 and 12 for speed 6, which is around 500 feet per minute, and speed 7, around 520 feet per minute. This allowed me to get the force and water level at all three speeds in my data tables. From there, I would reset speed to 0 and then wait for 1 more minute. Then I would stop the wind tunnel and I would go back to the force load cell and record the force again. This allowed me to record force drift and gave me a quantification of uncertainty for my data analysis. From there, I would stop the run and rename the data file, and then I would repeat these steps for the other nozzles. At this point, I would also like to thank Professor Ivalo Nedyalkov and Professor Christopher White from the University of New Hampshire for allowing me and guiding me through the use of the University of New Hampshire wind tunnel at Kingsbury Hall, and for teaching me and helping me understand certain aerospace concepts required for me to understand how the testing process worked. Without their help, none of this would have been possible. Moving on to data analysis, the following equations allowed for the data analysis: the ideal gas law equation, the Bernoulli equation, and the Reynolds number equation. Looking at the data generated from the wind tunnel testing, for 0% truncation, at a speed setting of 5, there was a drag force of 9.5 newtons, at a speed setting of 6, there was a drag force of 14.01 newtons, and at a speed setting of 7, there was a drag force of 19.2 newtons. Using the other data generated from the testing, I was able to calculate the coefficient of drag, and for 0% truncation, the coefficient of drag was around 0.2 for all speeds. Looking at the results for 20% truncation, at speed setting 5, there was a drag force of 10.5 newtons, at speed setting 6, there was a drag force of 15.01 newtons, and at speed setting 7, there was a drag force of 20.5 newtons. The coefficient of drag was around 20.225 for all speeds. Looking at the results for 40% truncation, we had very similar numbers, with at speed setting 5 a drag force of 10.5 newtons, at speed setting 6 a drag force of 15.02 newtons, and at speed setting 7 a drag force of 20.7 newtons. The overall coefficient of drag was around 0.21 for all speeds. Looking at 60% truncation, it had a drag force of 8.5 newtons at speed 5, 12.25 at speed 6, and 17.01 at speed 7. And it maintained a coefficient of drag of around 0.021 across all speeds. And then finally, looking at 80% truncation data, it had a drag force of 8.4 newtons at speed 5, 12.2 at speed 6, and 16.7 at speed 7, with a coefficient of drag of around 0.185 across all speeds. Now, when comparing all these nozzles all together, I originally compared the nozzles as a function of voltage and drag force, using the average voltage data from the data tracked by the voltage program and comparing it against the drag force. In this case, the nozzles with the lowest drag force at the same voltages would be the most efficient at converting the input to exhaust. The data unfortunately showed that there was no statistically significant difference between the 60% truncation and the 80% truncation. So based on a recommendation from Professor Nedyalkov to get a more quantitative analysis and more precise comparison, I used the formulas referenced in the previous section to calculate the drag coefficient and Reynolds number for each nozzle. The drag coefficient being the ratio of the drag on a body moving through air to the product of the velocity and surface area of the body, and the Reynolds number basically being a quantification of the turbulence of the fluid. By comparing the drag coefficient to the Reynolds number, the results showed that the 60% model offered a statistically significantly lower drag coefficient at all quantifications of turbulence, and as an extension, all speeds, meaning that the 60% nozzle was the most efficient at converting the wind coming in from the tunnel through output exhaust. So to summarize, the results indicated that the optimized Aerospike nozzle featured roused contour with 60% truncation. Originally, the nozzles were compared as a function of the voltage and the force applied on the nozzle by the wind, but seeing that there was no statistically significant difference between 60 and 80%, they were compared as a function of Reynolds number and the drag coefficient, allowing us to see that the 60% model offered a statistically significantly lower drag coefficient at all quantifications of turbulence, meaning that it was the most optimized choice for truncation. In the end, this design allows for altitude compensation, meaning that it can adapt to all altitudes and not lose efficiency at any atmosphere level. The truncation also allows for decreased weight, which will allow for better performance. By optimizing Aerospike nozzles, we can account for the shortcomings of the standard de Laval nozzles and design a more fuel-efficient, higher specific impulse rockets that will help us explore the universe. This research can hopefully help rocketeers in the future build more practical altitude compensating rockets that can hopefully achieve single-stage to orbit flights. In the future, to expand on this project, I would experiment with computational fluid dynamics to optimize for cooling, which is another issue that Aerospikes face. I would also redo my wind tunnel testing with more points to connect to the manometer so that I can quantify the pressure at more points across the nozzle's surface. Thank you.